All right, guys, happy Sunday. Thanks for coming down. It's a little earlier than I normally do my review, but because I have to do another review later for my other class, I thought I better start early. It's going to be kind of a long day, and I need to give myself a few breaks too. So, anyway, so that it's good that you're all here. I am recording this. If you need to leave early, I will send out a YouTube video of this session once it's all done. If you're out there in Zoom land and you have questions, just use your microphone to speak up and let me know. I might miss any notes in the chat because I'm just using my little phone today to record this. Um, and my game plan for the review is mostly to do a bunch of practice problems. So we've got a couple people in Zoom, a couple people here in person. And so between just a small group of us today, I'm hoping that we'll be able to solve these problems together. There are 20 problems in the review packet here, and I'm going to be going through them in somewhat of a random order, just kind of based on what I feel like we should look at. But my hope is that I will have done most of them, if not all of them, before I'm done with tomorrow's review. So I'm reviewing today and tomorrow, and I'll try and do different problems for the two sessions. Also, just a reminder that starting today, anytime between now and our final, you're welcome to come in and do your proofs ahead of time. You don't have to do that, but if you would benefit from just having that off of your radar so you don't have to think about it again, you are welcome to come in during my office hours. So, for example, today, I don't have office hours until this evening, and that's because I'm doing review sessions until late afternoon today. So I'll be busy until this evening, but you could come in this evening if you wanted to, or tomorrow, or on Tuesday before the exam. So you're certainly welcome to do that. Um, and yeah, ask questions during the office hours as well, and just hang out and study. I think it's going to be kind of a madhouse around here for a couple of days, especially tomorrow and Tuesday. So just bear that in mind. I'll do my best to find nice, quiet places for you guys to get your work done. Um,
Dr.
yes, question?
Uh, is it called final review or review session final with
Review
class?
session is the one I'm looking at, is where these problems are coming from. It's called in the Canvas, it's called the review session. And it also has solutions there. So there's two different documents. One of them has
Okay.
the solutions and one of them doesn't.
Okay.
Find it?
It says review session final solutions. Is that the one?
No, it says final exam review session problems solution.
Oh.
That's what I'm going on. There's 20 problems.
Okay. Okay. I see it. Okay.
Yeah. Got it?
Yeah. Yeah.
Okay, great. I will write these questions on the board though, just so we have them to look at as we're going along. And I'm going to mix up the topics a bit. Remember, on your final, you're probably going to have more points that you can do than what I'm going to grade it out of. So you will have some flexibility with that. Also, don't forget that I'd like to give you a little bit of extra time. So try not to be rushing to get out. If you have time to spare, it'd be great. That way you don't get yourself kind of stressed out about it. So, but other than that, it should be like a similar format to the midterms. It's just going to be longer. That's all, because there's more topics, obviously, and we have more time. So you should expect more questions to do. And like I said, you'll probably be able to throw something away somewhere along the line and not get hurt too badly by that. So, okay, well, and we're not going to be able to do an example of absolutely everything in the review session, but I'm going to try to hit some highlights as we go along. I'm going to start with just number one, but I will probably start going out of order before too long. So I'm going to take problem number one from this review session problems, and this will hopefully get our juices fired up this morning. It's a little early for me too. I got to get myself awake. So, how many ways are there to pick 8 balls from a pile of identical red, white, and blue balls, plus 1 pink ball and 1 tan ball. And the question is clarified that the order that the balls are selected in does not matter. Only the actual colors that you end up with is what matters. Okay, and it says that there's a pile of identical red, white, and blue balls. I probably should have said how many of those balls there are, but we can assume there's more than 8 of each of those. If there was a limitation, if there were only 5 identical red balls, then that would be a constraint that would be imposed on this problem. So a lot of times with these counting problems, this is what we're asking for, how many ways, right? Counting this thing. I like to ask the 2 questions that we regularly discuss. One is, does the order matter? And that's what was clarified in the question. It says here, the order that the balls is selected in does not matter, only their color matters. Okay, so the order does not matter. In this problem, the answer here is no. And then the second question is repetition allowed? And the unfortunate news about these 2 questions, guys, is that a lot of times the answers are not a clear-cut yes or no. It could be the order sort of matters, or it could be repetition is sort of allowed. And I would actually argue that in this case, repetition is sort of allowed, because you have identical red, white, and blue balls. So I can repeat the same ball, and we do care about the color of these balls, and we can repeat those colors, at least some of them. But then we cannot repeat the pink or the tan colors. So in this case, you might say that the answer is sort of. If you wanted to, you could answer this question as a yes, with the caveat that there's a constraint. So repetition is allowed in some degree here, guys, but it's just not fully allowed, because we have, maybe put an asterisk next to it. We have a little bit of a constraint. So, except for pink or tan balls. So we can't repeat those, but we could repeat the other colors if we wanted to. Okay. So there's more than one way, in my opinion, to sort of frame this problem or to set it up, but just big picture wise, what type of technique might you be thinking about when repetition is allowed and when order doesn't matter? Now, if you need to, go back and try to remember an example. Like, I like to have like a classic example of each of these scenarios. So like if repetition was allowed and order does matter, I think about things like license plates. Okay, license plates, because you can reuse the same characters, but the order of the characters in that license plate matters, right? If repetition was not allowed, but the order did matter, I tend to think about something like arranging photographs. So now there's no repeated object in the picture, but the order does matter. So, you can try to have like a standard example of the different scenarios here so that you can compare your problem with that problem. But in the case of repetition being allowed and order doesn't matter, the standard example that we used to introduce that idea was going into a grocery store and picking out types of fruit, pieces of fruit. And so this problem, the question is, is this problem like, is it more like license plates? Is it more like photographs? Is it more like buying pieces of fruit, or is it more like, I guess the other one would be playing cards, poker cards. But because of this yes and no like this, it's sort of more like the buying fruit example. And what was the technique that we used to solve that problem, if you remember?
Stars and bars.
The stars and bars technique, right? So we would be thinking about using stars and bars to solve a problem like this, simply based on the answer here. So stars and bars. And now what we need to do is figure out, essentially the bars are used to create bins that separates the different types of objects. So we could have a bar here, and then we could put, the red balls, maybe in the first part, right? And then we could have another bar that separates out the white balls. And then to the right of that, we could put the blue balls. Somebody trying to say something out there? So far, so good?
Oh, sorry, I need to mute myself. My bad.
No problem, no problem. And then the blue balls would be in the next bin. And if we wanted to, we could even make a bin. We could make bins for the pink ball and the tan ball. So there's pink here, and there's tan here. And that would be one way to do this. Now, some of you might be thinking you have another idea about how we could handle the pink and the tan balls. But for the moment, this would be reasonable, and we could just be assigning variables to the number of balls here. There'd be something like 5 of these things. Do I have all the colors? Yeah. Red, white, blue, pink, and tan. Oh, you know what? I forgot the lavender ball. I was just not reading my question carefully enough. There's also supposed to be, I'm going to go back to the question, guys, so it fits with what's in the review packet. There's also one lavender ball. My fault. I forgot about the lavender ball. So let's put the lavender ball in here as well. I actually, in my solution to this problem, I put the lavender ball as the 5th one, and then the tan one was the 6th one. So let's do it like that, just so it's consistent with my notes. Sorry about that. So we have a lavender ball as well that we potentially could use. So if we were setting up this problem using stars and bars, what we could say is there are 5 bars. As you can see, there's 5 bars. And the number of stars is always how many objects you need to take, whether it's pieces of fruit or, in this case, the balls. Here we want 8 balls. So the 8 balls become the stars. So this is a problem that would have 8 stars and 5 bars. So would the answer to this problem, so then the answer with stars and bars is usually to add them up, stars plus bars, and then choose bars. I usually like to choose the bars, although you could choose the stars instead. So in this case, that would give me 8 plus 5, choose 5, which is 13, choose 5. And would that be the answer then? What is that not taking into account?
That we only have like one pink.
Yeah, we only have 1 pink, 1 lavender, and 1 tan ball, and those are actually constraints. So we can think of this actually as an equation. X1, X2, X3, X4, X5, and X6. They have to add up to 8. But there's a constraint here, which is that X4 has to be at most 1, X5 has to be at most 1, and X6 has to be at most 1. So this 13 choose 5 would be ignoring those constraints. So this is without constraints, that we would have 13 choose 5 ways to choose these balls. Okay, but the issue is that we can have at most 1 of the pink, lavender, and tan balls. So what I'm going to want to do is create violations that can be subtracted from this unrestricted total, right? So let's think for a minute about the violations. It's kind of a standard technique, guys, is to use the subtraction trick. You take the number of solutions without any constraints, and then you subtract violations from that. So in this case, we have actually 3 types of violations, and I could set them up as sets. So I'm going to frame it this way: sets A, B, and C. A would be the set of solutions with X4 being at least 2. So that would be a violation of the pink ball constraint, right? You can have at most 1 pink ball. Well, these are solutions with at least 2 pink balls. And then set B would be solutions with at least 2 lavender balls. And then set 3 would be, the third set would be solutions with at least 2 tan balls. And so our final answer should just be 13 choose 5 minus any of these violations, right? So our answer, if I want to write it out, should be 13 choose 5 minus, it's actually the union of these sets. So we like to frame that as a union of sets, and we're looking at the size of that because you could have multiple violations at once. So they can overlap a little bit. So what are we going to have to do to calculate the size of the union? The inclusion-exclusion principle, exactly. So this could be thought of as 13 choose 5 minus, and then I'm going to work out the inclusion-exclusion principle. Maybe I will come back up here where I have more room. Okay, so this is going to be 13 choose 5 minus the quantity of, so now I'm going to write out the entire list of terms here. The size of the individual sets get added together first. And then we subtract the 2-way intersections. So the A intersect B, A intersect C, and B intersect C. And then we go back and add back in the 3-way intersection of A, B, and C. So it becomes several terms, and be sure to use brackets on this because there's a minus that has to be distributed to all of these terms. Okay, each one of these 1, 2, 3, 4, 5, 6, 7 terms over here is actually just another stars and bars problem, right? So the 13 choose 5 that we're starting with is now going to be with minus a bunch of stars and bars calculations. For the size of A, just to take it a little slow at the beginning, we're looking at solutions where X4 is at least 2. So what you could remember is that's like going in and grabbing 2 apples from the store and taking them outside without making any choices at all. You're just taking away 2 of your stars, basically. So instead of 8 stars, now you would only have 6 stars. You still have these 5 bars, so that would be a total of 11 objects, and you're choosing the 5 bars again. Okay? And then actually the size of B and the size of C is exactly the same. So 11 choose 5 and 11 choose 5. So you might just make a quick note. I like it when a little explanation is given here. So on this first 11 choose 5, I might say remove 2, what would it be, pink balls. So now you have 5 bars and 6 stars. It doesn't have to be a long-winded explanation, but just something so I kind of know where the 11 comes from, just so I can have a justification. And also, the other reason for writing that down is that if you accidentally make a typo or miswrite it, if you've got the words to explain it there, I can still give you credit for it. If the work is not explained and it's wrong, then my hands are really tied. I don't know how to justify the partial credit. So be sure to write some notes here as we're going along. And let's keep going. If we want to look at the two-way intersection of A and B, now I'm going to take at least 2 pink balls and at least 2 lavender balls. So I've actually removed 4 balls, and that leaves me only 4 more balls to go. And together with my 5 bars, I should have 9 choose 5. So here we remove 2 pink and 2 lavender balls, and that leaves me with 5 bars and 4 stars. And each of these two-way intersections is going to be 9 choose 5. Okay, so we'll have that for each of those. And finally, the three-way intersection is also possible. We could have 2 pinks, 2 tans, and 2 lavenders chosen. And so we have to add that back in, and that should just be 7 choose 5. So now you're taking away 6 balls. Remove 6 balls. I'm going to be a little brief here because I'm out of room. But at that point, you have just 5 bars and only 2 more balls to pick. Okay, so this would be a perfectly good answer. Remember, this is going to be a no calculator exam, so I'm not expecting you to crunch the numbers of these kinds of expressions. You can just write them down like so. Okay, what do you guys think? Any comments, any questions on that? Can anybody think of a different way of doing the problem? That would, instead of subtracting violations, would there be maybe a different way to approach this? I personally think this is a great way to do it. If this is what you're comfortable with, it's totally fine.
Is it possible, since we know that it's just I'm understanding the problem correctly, right? Just 1 pink ball, one lavender, 1 tan. So maybe we just need to find the solutions for 5 balls total of the other colors.
Yeah, we could actually just you're on the right track, Sergio, is what I'm thinking about, which is that there aren't that many different cases here. You could go back and say, well, what if I don't use any of the lavender, tan, or pink balls, and I just make my solution only out of the red, white, and blue balls. So I could do, so let me write this down. So this is sort of an alternative solution. An alternate solution would be to say, what if I took, so basically what I'm going to suggest here is a solution by cases. And your cases would be, case 1 would be no special balls, no special colors. So in other words, you're making your solution out of only the red, white, and blue balls. If you did that, you still have a stars and bars here, but you wouldn't be using X4, X5, and X6. You would just make piles of the red, white, and blue balls using 2 bars, and you still have the 8 stars. So I won't fully write this out, but you could imagine doing the 8 stars and the 2 bars where you're only using reds, whites, and blues. Okay, and then you could have a case 2 where you say use the pink only as a special color. Okay, if you say yes, I'm going to use the pink ball, but I'm not going to use the lavender or the tan ball, well, that's one of your balls. And now you just pick 7 of the red, white, and blue balls. And you still have just the 2 bars separating the reds from the whites from the blues. Okay? And then you could have case 3 would be use the lavender only. And that would actually give you the same number, 7 plus 2, choose 2. And then case 4 would be, use the tan ball only. You only have one of these extra balls, so you don't have to decide how many of the tan balls or the lavender balls or the pink balls you're going to use. You're either using that special colored ball or you aren't. So that would be some of the cases, but of course, there's even more cases because you could take both the pink and the lavender ball. So this case 5 would be use pink and lavender. So now you only need 6 other balls from the red, whites, and blues. So that's 6 choose 2, choose 2. 6 plus 2, choose 2. And just so on like that, right? The very last case, which I think is case 8 actually, would be to use all special colors, which means you grabbed the pink ball and the tan ball and the lavender ball. That leaves you only 5 more balls from the reds, whites, and blues to choose. And what you could now do, guys, is add up these 8 numbers. Okay, it's about the same number of terms as we had over here, but instead of subtracting the violations, this one is just a more direct approach, adding up these cases. Does that make sense? So that would be like another way to do the problem if you wanted to. Comments or questions on this one? It doesn't hurt to take questions like this and just for yourself imagine variations of it. What if the red, white, and blue balls were not identical? In that case, they would be on no different footing than the pink, the tan, and the lavender ball, right? Because you would have one of each of these balls. As soon as the balls are not identical, it doesn't even matter that they're red. It just matters, okay, I have a bunch of different balls that are some different shades of red, right? But we're counting them all as distinct from each other. In that case, we really would have to clarify how many of each kind we had, because if the balls were distinct, I wouldn't know how to answer this question unless I knew how many of these there were, how many of these, and how many of these there were. So you'd have to be told that. I have 5 different shades of red balls, one of each. And I have 5 different shades of white balls, one of each of those shades, and so on. So you'd get a total number of balls, and then you'd literally just choose 8. Your answer would just be the total choose 8. You wouldn't care about creating different bins for different colors because they're just all distinct balls. Does that make sense? Or the other thing you could do is say, well, what if the order did matter? What if you're putting these balls into a row and you want to know which ball comes first, which ball comes second, which ball comes third, and so on? That would be, again, a different solution. It doesn't take much to change the outcome of these problems and even the approach to these problems. So I encourage you to explore some of those variations, and then, if you try one and aren't sure you're comfortable with it, you can always ask me to. Maybe I'll find out that you've come up with a problem that's just too hard to do, but it's still worth playing that exercise. And you can do this with each other as well. Just make questions for each other and see if you can work them out together. Okay. If there's nothing else on that problem, I'll cross that one off of our list. And I'll erase this one, and let's go to something else. As I said, I'm going to jump around a little bit. So I think I'm going to jump to problem number 6 on this handout now. I'll write it down, and then we can think about it together. So what is the fewest number of time slots needed to schedule finals for Math 302, 402, 407, 414, 417, 425, 430, and 471 if there are, and then I have a list of conditions here, so we can jot these down. No students taking both 302 and 471. Okay, so we have none of those. And then also, I'll just use a ditto symbol here, guys, to reduce some of the writing. There's no students taking 402 and 471. And then there's no students taking both 414 and 417. And then there's no students taking both 414 and 425. And there's no students taking both, there's a lot of writing here, guys, sorry. Taking both 302 and 402. I've got to make the problem big enough that you can't just sort of do it in your head kind of thing. 402 and 302, and then there's no students taking both 302 and 407. And finally, there's no students taking both 407 and 414. So there's no students taking common to any of these pairs, but then it says there are common students in every other pair that we have. Okay, so it's kind of a long question to write it all out, but maybe while I'm erasing here, you can think about what would be an approach to solving this kind of a problem. So how many different final exam slots do we need? So we kind of have to understand that a student cannot be in two places at once. So you cannot offer the final for two classes at the same time if there is a common student in both of those classes. So you have to schedule different times for those people. So it's a good real world application problem, obviously, of something like this. Any thoughts on maybe what would be a approach that we could use, strategy?
Forbidden position.
Okay, so forbidden positions is one thought. How would you set up your grid? So forbidden positions has a grid, and like you list out something on the columns and something on the rows, and then you put the X's in the picture. And it's definitely something we want to make sure we know how to do. How would we set it up in this case? They didn't get very specific about the time slots, by the way. It doesn't say, oh, it's from 8 to 9 and then from 9 to 10. It's not really. So we don't have like a set of times that we can spell out. It's just a list of classes here. Any other thoughts?
What if we just put all the classes in both the rows and columns, and then if there exists a student who is in both, we fill in that cell?
So we could try to list all of the classes. Let me see if I'm getting this. 302, 402, 407, and so on. And then 302, 402, 407, and so on. And so what you're saying is, so there's if there is a student in both classes, so for example, it looks like there is a common student in, let's say, 407 and 471. Okay, so then that would mean that 407 and 471, I'm just trying to get the rough idea of this. 407 and 471, you would put an X. Is that kind of the way you're thinking about it, Hamza?
Yeah, so like if there's a student who's common in both, then you fill in that, and then that's a forbidden position, I guess, right?
Right. So kind of like what I just did. I
Exactly,
made a
exactly.
forbidden position between 407 and 471 here. So at the end of the day, I'll have a bunch of X's. What about 302 and 302? What do I do with that? Also, so eventually, remember how we did this? We would choose, you just try to make a choice that avoids all of the X's somehow. What would this actually mean? Like if these were different time slots, then I'd say, oh, we're gonna do the 402 final at 8 o'clock, and then we're gonna do the 430 final at 9 o'clock, and the 302 final at 10 o'clock, and that would make sense to me. But I don't understand how I'm interpreting like this choice of dots. Like, what does this actually mean? If I put a 302, 402, and put a dot there, that means that, okay, I can offer that final at the same time. But then, like on the next row, I've got 407 with a dot onto, 402 with a dot onto some other class. It's like, I don't know if I understand what the diagram means.
Oh, is it that we're trying to figure out which exams can be scheduled at the same time? Maybe that's what he was trying to do.
Yeah, I mean, like, so that's true. We could say, yeah, 302 and 402, they could be scheduled at the same time. But that's not the only two classes that could maybe be scheduled at the same time. I could probably do, actually, I can't do, that's with in X, isn't it? Based on my information. But it wouldn't be giving me all of the possibilities. So I'm going to throw something out to you guys here, which is that I actually don't really think this is a forbidden positions problem. Even though it kind of looks like it initially, if I had time slots and we were like, oh, we can't offer the 302 and the 402 final at 8 a.m., then that would be more like forbidden positions. I would be crossing off, those particular positions in the grid. But I don't have time slots. We've never set up a forbidden positions problem with the same quantities on both the columns and the rows. So this is, at the very least, this is very weird to set it up this way. I actually think that this problem makes more sense to think about on a completely different topic. But this is a good first conversation, because I do think it would be natural to look at this and say, oh yes, this is a forbidden positions problem. But I actually feel like there's something else that's maybe a little more gets to the point of what we're trying to do here. I'm going to draw a graph, okay? And I'm going to try to do a little bit of graph theory with this. I'm going to make a vertex for every one of these classes. So let's see if I can convince you that graph theory is a great way to go here. So I'm going to make a vertex for every class. So I have a dot for 302, and then I'm going to make another one for 402, and then 407. I'll kind of put them in a circle for now. 414, 417, 425, 430, and 471. And what I'm going to do, guys, is I'm going to draw an edge. I'm going to draw an edge between two of these vertices if there is a common student among those two classes. So if I look at 302, there's nobody in common between 302 and 471 or 402 or 407. I'm looking everywhere I see 302 listed. There is no common student between 302 and 471, 402, and 407. But that means that there is a common student between 302 and 414, 302 and 417, and 302 and 425, and even 302 and 430. There is a common student. I'm going to draw those edges to show that there is a common student there. Now let's do the same thing with 402. There is no common student between 402 and 471 or 402 and 302. So I'll have no edges between 402 and 302 or 402 and 471, but all of these others I will. So there is common students between 402 and all of these other classes. So I'm going to draw all of these other edges in right there. Okay, so it's going to have a lot of edges on this graph actually. Okay, let's go to 407. 407 is mentioned down here. There is no common student in 407 with 302 and 414. So I should not have any edges between 407 and 302. I mean, there's no common student there, and there's also no common student here, but every other class there is. So there is a common student 407 and 417. There's a common student 407 and 425. And there's a common student between 407 and 430. And there is also a common student between 407 and 471. Okay? I'm just going down the line here. I'm kind of going in numerical order. So I've kind of done all of the 302, 402, and 407 edges. Now let's look at 414. 414 is also mentioned there is no common student with 417, so I don't want that edge. And we've already talked about 407. So it's really just for 417, it's just 414. Sorry, for 414, it's just 417 that doesn't have an edge. So there's no edge there because there's no common students. But there will be common students to 425. There will be common students to 430. And there will be common students to 471. So far, so good? I'm drawing edges when there is a common student between those classes. So the non-edges are basically the edges that are mentioned here. Okay, let's look at 417. 417 has no common students with 414, but it does have common students with all of these other courses. So there should be an edge to 425, to 430, and to 471, as well as the other ones that we did earlier.
Dr. Annan, I think
Yes.
you drew an edge between 414 and 425, but
And I shouldn't have done that. Yeah, let me take that edge out. Thank you. Thank you, thank you, thank you. I'll just blame it on being early in the morning still for me. Yeah, so there we go. We took off that edge. All right. So I did the 417. 425, really the only non-edge is with 414. We actually have to have all of the others. So 425 to 430 and 425 to 471. Definitely have to have that. And then for 430, actually 430 is never mentioned as having no common students. That means that there is somebody taking 430 along with each of the other classes. So I'll draw the edge from 430 to 471. And that should do it. That should do it. So this is a graph, and anytime two vertices are joined by an edge, it means that there is a common student, which actually means that they need to be offered at different times. The finals need to be offered at different times. So now my question for you about this is, what am I asking you about for this graph? adjacent vertices have to be offered at different times. So if there's an edge 302 to 414, those finals have to be offered at different times because there is a student common to both of those classes. What concept, it's pretty recent, what concept have we learned about graphs that we would be looking into here on this problem?
Oh, like the equivalent colorings, like the color is the time slot.
Colorings. Yes, this has to do with coloring this graph, right? So two adjacent vertices should be colored with different colors. That just means that they're going to have different time slots, right? So like the 8 a.m. exam might be colored blue, and the 9 a.m. exam might be colored red, and the 10 a.m. exam might be colored green, and so on. Yeah, we're really asking about the chromatic number of this graph, right? It is a chromatic number problem. So that's the subtle thing here. This is about chromatic number for this graph. Okay, so as an example of this, notice that the 430 was connected to everything. So whatever color I give it, maybe I'll color this one yellow. I cannot use yellow anywhere else again in the graph. I will have to use entirely different colors everywhere else. And then, so we could actually try to use that algorithm where we reuse the colors as much as possible as we go around. So like when I go to, notice I'm picking on the vertices that have high degree first. So 430 has the highest degree of them all. I picked yellow. 425, maybe I pick blue. It has blue because it has an edge to every other vertex except 414. So what I'm going to do is I'm going to say, okay, that means I can use the same color for 414, which just means you're giving those finals at the same time, right? And then we have to look at, let's say, 417. We can see that 417 is connected to both 425 and 430 and 414. So we will need a different color for 417. Maybe I choose green. Okay, so we'd use a different color on that one. And then is there anything else that could also be green? Well, actually, no, because all of the other vertices are connected to 417. So we have to, the only one that's not is the 414, but I can't use the same color for 414 that I did for 417 because they're both, so yeah, see, I need three different colors here, right? And then this 414, you can imagine you're reusing one of those colors. It really doesn't matter which one. Okay, now there are vertices that are connected to all three of these colors, such as 402. 402 is connected to 430 and 425 and 417, as you can see. So we need a fourth color, right? So for 402, maybe we use, I don't know, white. Okay, so we pick a different color for that one. But I see that I can use that same color white on several of these other vertices, such as 302 and even 471 can also be white because none of those are connected to each other. So let's put all of those finals at the same time. And then last but not least, I still have to color 407. I can't use white. I can't use green. I can't use blue. And I can't use yellow. I need a fifth color in order to do that. So maybe I pick, I don't know, purple, something like that. So we would need a fifth color for that. Does that make some sense? In my solution, I made a note here that actually 407, that there's actually a K5 here. If you actually can see a subgraph of K5, then you know you need 5 colors. You can't do better than 5 colors because the chromatic number of K5 is 5. And if you look at 407, 417, 425, 430, and 471, I believe that you have every possible edge among any of those. So you can kind of check that you do. And because of that, you know that 5 colors is the best you can do. So the chromatic number of this graph would be 5, and that is the number of time slots that you need. What do you guys think? Does that make sense? It's kind of a little bit of a tricky chromatic number problem. People, I find usually they look at this question and they're like, oh yeah, that's forbidden positions. But then it actually requires something different. Okay. So that was number 6. Any questions on that?
So in a problem, if it asks for like the fewest possible of something, is that a good sign that you should be thinking about chromatic number?
You know, I think that makes sense because you know, the chromatic number is the fewest number of colors that you need to color a graph with. So it certainly is aligned to that. But you know, I'd be a little bit careful. I don't like to make huge blanket statements like that, because I could also say, well, how many people need to be in a room in order for you to guarantee that 2 of them have the same birthday? And that is actually a pigeonhole principle problem. So again, what's the fewest number of people that we need to be in the room so that you guarantee 2 of them have the same birthday is much more naturally viewed as a application of the pigeonhole principle. So be a little careful about drawing sweeping conclusions here, but your overall insight, Hamza, is really good, I think.
Thank you.
You bet, you bet. Okay, let's do another one. Yeah, let me do another problem. I'm going to do number 9 on the handout. I'm trying to jump around so that if I don't get done with all of these today, then tomorrow I can come back with cycle back through some of these examples again. So on number 9, I'm going to consider the graph here. I'm going to draw the graph on the board for you guys. There are basically 2 circles. One of them is inside of the other one. You have 2 circles like that, and then there's a vertex directly in the middle of the whole picture, kind of right on the bullseye. And then on both the inside and outside circles, we have vertices on the north, south, east, and west edges of the circle. Okay, so something like that. And then we actually have edges that connect the outside circle to the inside circle, kind of going along those 4 compass directions. But then there's a little bit more to the picture than that. We also have 2 vertices on opposite sides of the outer circle in the northeast and southwest sides. And also on the inside circle, on the northwest and southeast sides, we have another vertex. And actually on that inside circle, we have a couple of edges that go into the center vertex from there. So I think I got my picture fully drawn. Let me label these vertices. So on the outside circle, on the compass directions, I have A, B, C, and D going around like that. And then on the inside circle, I have E, and then F, and then G, and then H, and then I, and then J. So E, F, G, H, I, J going all the way around clockwise, starting at the top. And then K is in the center. And then I didn't use an L for some reason. I went to M and N for these catty corner vertices like that. And I'm going to ask you guys about 4 different questions about this graph. So the first question is there an Eulerian trail in this graph? we had a midterm not too long ago. I guess it was before Thanksgiving, but hopefully people still have a little bit of fresh thoughts about some of these graph theory questions. Do you remember what the conditions are for Eulerian trails to exist? Pretty straightforward, Kevin.
It's close Aurelian trail if the every vertex have even degree.
Okay, a closed Eulerian trail would require every vertex to have even degree, and then for the open Eulerian trail, what would it be?
Exactly 2 vertices have odd
Odd degree.
a degree. Yeah.
Exactly. So for an open Eulerian trail, exactly 2 vertices would have to have odd degree. You should be able to glance at a graph and pretty quickly figure that out. And then if I ask you to produce, usually if the answer is yes, I will ask you to produce it. So you make sure you know the process for actually writing out the Eulerian trail. I think on the midterm this went pretty well. I had a problem like that. But in this case, yeah, what are you going to tell me about this case? Is there going to be an Eulerian trail of any kind here? I just have to look at, as Kevin said, I just have to look at the degrees of these vertices, and I actually see a lot of vertices that have degree 3, right? More than 2 vertices of degree 3. That rules out any kind of Eulerian trail whatsoever. So no, since we have more than two vertices of odd degree. And that would be more than sufficient. If you wanted to actually give me some of those vertices, you could. It wouldn't have to be a comprehensive list, but even just A, B, and C are going to have degree 3, and many others as well. So that's an easy one. Not too crazy there. Let's go to part B. Part B is going to ask us, is there a Hamilton cycle? This is usually a little bit more challenging question because we don't have any easy theorems characterizing Hamilton cycles. There's no if and only if conditions. We kind of have to go more to like a grassroots approach. The idea being that for a Hamilton cycle to exist, exactly 2 edges that are incident with each vertex would have to be used. And so what I like to do is to just try to start doing it. I like to just start trying to make my Hamilton cycle, and I'll either be successful, in which case I can just exhibit the cycle, or I'll run into a contradiction somewhere, and at that point I can try to write it up. But vertices of degree 2 are going to be very helpful because you must use both of the edges that are incident with the vertex of degree 2. So a Hamilton cycle, I don't know the answer to this question yet, but a Hamilton cycle must use several of the edges in this graph we can already be guaranteed of. So for example, vertex M has degree 2, so I'll draw these in blue. Guys, just like with the last midterm, I'd recommend bringing some colored pens with you on Tuesday, just so you can mark up your graphs a little bit. So AM and MB, right? What would be some other edges that we could put into this list?
Not H. DN and NC.
DN and NC, right? So let's do that. DN and NC, I agree. I'll go ahead and shade those in. And are there any others?
JE and JI.
What's the degree of J? Careful.
Never mind.
That's okay. That's okay. I don't think we can say JE and JI.
The KJ and the KG.
Okay, KJ and KG. Right. I think that's what you meant. Yeah. So KJ and KG are also required to be used because vertex K has degree 2. Are there any others that are guaranteed to be used? I don't think so. The remaining vertices all have degree 3, so you'll have choices about how to enter and leave the rest of those vertices. Remember, another key thing about Hamilton cycles is that you cannot have any premature subcycles. I noticed, for example, that I'm only 2 edges away from actually filling out the entire outer circle. And that would be bad because that would not create a Hamilton cycle. You would be missing all of the inside vertices by doing that. So you cannot have any premature subcycles. So I like to take advantage of I like to take advantage of the degree 2 vertices, which is what we already did. Okay. The other thing I like to take advantage of is no premature subcycles can be found. And then the other thing that we can take advantage of is the symmetry of this picture. And actually, if you sort of tilted this thing so that the edge JK to K and KG were straight up and down, you'd have a completely symmetrical figure. There's basically an axis of symmetry kind of going off on this tilted angle here. So I think I would recommend pursuing the point that I made a few minutes ago, which is that you cannot use both AD and BC, or you would have a premature subcycle. So we cannot use, I'll go ahead and write it down. We cannot use both AD and BC, or we'll have a premature subcycle. And in that case, I like to list the cycle if I can, if it's not too much work. So the outside cycle would be from A to M to B to C to N to D and then back to A again. So that would be a premature cycle. It's not covering all of the vertices. So without loss of generality, I can assume that one of these 2 edges is not used, right? So I could assume without loss of generality, assume that AD is not used. Okay, so that's not something that's forced on us, but we can more or less assume we're not going to use AD because otherwise we would, if we used both AD and BC, we'd have a premature cycle. Okay, the minute that I take off edge AD, what else does that tell us? What's the domino effect of that?
AE and DI cannot be used.
AE and DI
Must be used.
Must be used, right? So AE, this one, must be used, and DI must be used, right? Because you've got to visit vertex D and vertex A. You have to have 2 edges that are colored blue that you're using. So we must use in this case AE and DI. Okay, so we're really filling this in pretty good. So we've got AD, we've got DI like so. Okay. And so far we haven't really gone into any cases. So sometimes you get to a point where it's like, I have to consider more than one possible option because I can't rule anything out. So far, we haven't done that. So far, we're just on a clear, clean path to getting to our conclusion. Anything else that maybe symmetry would allow us to do? If you kind of look at what's been shaded into blue already, does that create anything symmetrical here that we could take advantage of? Again, the axis of symmetry is really this sort of angle that's heading up towards 11 o'clock, towards the top left here. if you just kind of turn your head this way and you look at sort of the part that's in blue, what I'm seeing, I know I have to use either JI or JE, but I won't be using them both. And because it's symmetrical on the left side of that axis of symmetry compared with the right side of that axis of symmetry, I think we could, without loss of generality, pick either JI or JE to use, and then therefore not the other one. Okay, so again, by symmetry, I'm going to try to avoid overcomplicating it with cases if I don't need to. By symmetry, let's use the edge. I'll just use JI, I guess. It doesn't really matter. Let's use this edge JI right here. Go ahead and fill that one in, which means we cannot use JE. So we cannot use, in this case, we cannot use JE. So I can kind of semi-erase the edge JE if I want to. You may even decide on the exam, guys, that you want to take the graph and just redraw it in pencil to begin with, so you can like erase edges and stuff. Just be careful that you copy the graph correctly if you're going to do that. Okay, based on that, I'm now using JI but not JE. What else can I say? I still don't have a contradiction, but what else am I going to do?
You can't use IH.
Cannot use, so we cannot use IH, right? Because we've already used two of the edges that are incident with I. So we're kind of getting rid of IH here, right? And then what else can we say?
We must use EF.
And we must use EF. Thank you. Yes, exactly. So EF is right here. I'll color it in blue. And must use, we must use edge EF. Okay. Surely we're getting close to either having a Hamilton cycle or producing a contradiction. What else could we say at this point? Oh, I think I see it. I think I see the contradiction. It's not possible, guys.
The G is kind of blocking the way, so
Yeah, don't look at G. There's a different vertex that's basically going to give away the whole thing.
What's the F?
You could use F, but there's an even faster one. There's an even faster vertex that basically is immediately.
Oh, H has only 2 edges left.
H has only 2 edges left, so you have to use both of them. And then what will that create?
Subcycle.
A premature subcycle. Exactly. So now we must use HC and HG, which creates a premature subcycle. And then again, if possible, we should try to list it out. So I'll start at J to K to G to H, and then from H down to C, and then C goes over to N, and then from N to D. I guess this is a little longer than I thought. N goes to D, which goes to I, which goes back to J again. So that was a little longer to write it out, but if possible, it's good to do that. Does that look okay? That would not have been the only way to get a contradiction. If you didn't want to use the H, vertex H to argue it, you could do what Alyssa was kind of suggesting, which is if you look at vertex F, you can see that you cannot use FB, or you'll have a different premature cycle. So if you take that off, well, then you'd have to use FG like that, but that would mean you couldn't use GH, and now you've got a problem. This is a different kind of contradiction where you only have one remaining usable edge that is incident with a vertex. If there's any vertex in your graph, guys, of degree 1, or even if it has higher degree, if you've removed the possibility of using too many of its edges and you're down to only one incident edge, then there's no way to make your Hamilton cycle in that case either. So the answer for this is that there is no Hamilton cycle. I like this. This is about the right difficulty that I would ask you. I mean, I'm either this or probably not anything that's too much harder than this, but you know, you do have to think a little bit. You have to kind of know what the rules are and the tools that you have for Hamilton cycles. So again, if the answer is yes, the best way to explain it is to just show me the cycle. Just write out the vertices that form that cycle. Okay, I'm actually going to draw the whole graph back together again because I have another question for you. Still not done with this problem, guys. There's a few questions. The part C is going to ask you, what is the chromatic number of this graph? So I'm going to maybe ask that question here. So part C is, what is the chromatic number? So this is going to be the fewest number of colors. Whoops, I forgot to put this edge back. What is the fewest number of colors that we would need in order to color this graph? So that's a good question. Remember that the only graph that has a chromatic number of 1 is a graph with no edges. The only graphs that have a chromatic number of 2 are, which kind of graphs were those?
The
Trees.
it's the cycles one, right?
It has to do with that, but there's one word for this type of graph. I haven't mentioned it today. A graph that would have a chromatic number of 2 would always be a blank graph. Starts with a B.
Bipartite.
Bipartite.
Yeah, it's a bipartite graph. So bipartite graphs have 2 camps of vertices, and you can just make the colors those camps because there's no edges within a camp. So the thing about bipartite graphs is they have no cycles of odd length. So if this graph has no cycles of odd length, then we would be able to say that it's a bipartite graph, and therefore that it would have a chromatic number of 2. So does this graph have any cycles of odd length? I shouldn't have erased this thing down here. Maybe that was of odd length, I don't know. Well, unfortunately, I think this graph does have cycles of odd length. Even just up here in this corner from I to J to E, back to A to D to I. This is 1, 2, 3, 4, 5 edges. So that's a 5 cycle right there. Same thing over here. That's a 5 cycle. So this graph has odd cycles, which means it's not bipartite. So let's just write this down. So since G is not bipartite, and then you might explain why you know that. It has cycles of odd length. So it's not bipartite. So since it's not bipartite, its chromatic number must be at least 3. I mean, another way to explain it would be to just simply say you have a C5 graph as a subgraph. So just as an alternative, a C5 is a subgraph of G. I'm calling this whole graph G. So the chromatic number of G has to be at least as much as the chromatic number of any subgraph of G. Pretty sure this came up in the homework. That the chromatic number of a subgraph is always less than or equal to the chromatic number of a graph. And the chromatic number of Cn, we actually did this in class, that just depends on whether n is even or odd. For an odd cycle, the chromatic number is 3. So that's just another way of explaining why you know that this graph has a chromatic number of at least 3. So the question would be, well, could we actually do it with 3 colors or not? It might be that we need even more than 3. So the thing that would be the best way to convince me would be to maybe start trying to think about coloring it. Just see if you can do it, right? So I could take this graph and start assigning colors. Let me get rid of some of this extra writing. I could try to start assigning colors. So I could go use the algorithm that says just keep going around coloring the graph using as few colors as possible. So I could say, all right, vertex A, I'm going to start with yellow, and then anything next to that has to be different. So maybe for vertex B, I'll use blue. Or sorry, that's vertex M. For vertex M, I'll use blue. So A is yellow, M is blue, and then because B is not connected to A, I would go back to yellow again immediately. Right? And then because F is not connected to M, I go back to blue again immediately. So I keep reusing the colors as much as I can. But vertex E is connected to both A and F, which are already using the yellow and the blue. So now I need a different color. Maybe I can go to green. So I make that one green. And that makes sense because that's a 5 cycle. And we know that for that 5 cycle, we would need 3 colors. The real question is, can I do the rest of the graph with just those colors? So we can try. So let's see. Maybe I go to J. And for J, I'm going to go back to yellow again. Because I see that yellow is not connected. There's no yellow vertex connected to J. And then for K, I could go back to blue again. Okay. And then for vertex G, I could use either yellow or green. Maybe I just use green this time. You know, it's kind of a little bit of trial and error about this. But the point is, I'm reusing the same colors as much as I can. Vertex I could make that one blue. And then H could be yellow. And then, so here I have a yellow, here I have a yellow. So C, I could make that one green. And then I could go back to yellow again for vertex N, and then D could be green. And I think that works. The reason that this graph has a relatively low chromatic number is because the vertices all have low degree, right? It's not like that last problem with all the different classes where there were tons of edges and we needed 5 colors to color it. This one, we only needed 3 colors. So what I would probably say if I was solving this problem is phi of G is less than or equal to 3 since we achieved a coloring of G using only 3 colors. So I like to make these arguments in 2 parts. The chromatic number is at least 3, and then it's at most 3, and so hence we put those 2 together and conclude that the chromatic number is exactly equal to 3. That make a little bit of sense? Questions on that, guys? Comments? Okay. If not, I have one last thing I want to make sure everybody knows how to do. Part D of this question is to find a spanning tree for the graph. And this is where I think it really would be a good idea to have a pencil and have the graph drawn in pencil because you're going to be deleting edges. Remember that a tree is simply a connected graph with no cycles in it. One of the many ways we can think about a tree. A connected graph with no cycles. So I can take my graph, it's already connected, but the point is there are cycles here, and I need to remove edges until there are no cycles left. That's going to be how I do this. So I'm just going to, well, I guess what I would recommend is that we draw this graph again. So there's the outside circle. I'll do this quickly. And then there's the inside circle. And we have the 4 compass points on both circles. And then we have the 2 circles connected at those compass points. And then there's one more vertex in the center. And then we have this little axis of symmetry there. And then we have 2 more vertices like this. So just to redraw the graph. Okay. And A, B, C, D, E, F, G, H, I, J, and then K, and then M and N. So I get the whole thing labeled. I just wanted to have a fresh picture of the graph here. And we just need to remove edges. And I think I'm just going to have you guys tell me what to do. The point is we just want to remove the cycles. And as long as you take off an edge that's part of a cycle, you'll be good. All right, so somebody want to give me an edge to start with, to remove? BC? I'm going to take off BC. All right. Who wants to give me another edge?
Oh, like CD.
CD is not an edge.
Oh, I mean the NC.
NC. Okay, get rid of that one. Okay, as long as I'm taking away an edge that's part of a cycle, I'm removing what's called a non-bridge. So that's totally good. The main thing we don't want to do is remove a bridge. If you remove a bridge, remember what a bridge is. It's an edge that would disconnect the graph. If you remove the bridge, this will be disconnected and you won't have a tree. Okay, somebody want to give me another edge? Tons of choices here.
JK.
JK. All right, we'll get rid of JK. All right. Anybody in Zoom want to help me? I don't think they want to.
AM.
What was that? AM?
AM.
Yep. All right, I'll take off AM. I like that. This is actually a pretty easy process. Okay. You almost can't mess it up because as long as you keep the thing connected as you go, there's lots of right answers. Okay, somebody else want to help me? I still see lots of cycles. This is not hard, guys. Just give me anything you want quickly.
AD.
AD. All right, get rid of AD. Okay, what else can we get rid of?
EF.
EF. I was wondering when we were going to take off an edge from that inside circle. Okay. Are there any more cycles there? I don't think so. I think this is actually now a tree. Now there's a way to make sure you've got it right, which is if you count how many vertices you have. So this graph, the original graph has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 vertices. So this graph has 13 vertices. So does anybody remember how many edges there are in a tree compared to the number of vertices? It's n minus 1, right? There's always one less edge than the number of vertices. So you can just check, do I still have 12 edges here? And actually counting edges might be hard because the graph has a lot to it, but you can count the edges by using the handshaking theorem. So you could go around and figure out the degrees of the vertices. That's a 1, that's a 1, that's a 2, that's a 2, that's a 3, that's a 1, that's a 3, that's a 1, 1, 2, 3, 2, 2, and add up all those numbers and divide by 2. So 1 plus 1 plus 2 plus 1 plus 1 plus 2 is 8 on the outside. And then 2 plus 3 plus 3 is another 8. And 3 plus 2 plus 2 is 7. That's 23. And then the vertex in the center is one more. That's 24. If you divide that by 2, it is 12 edges. So you cannot remove any more edges than that. That would be the entire thing. Okay. So does that seem all right, guys? Okay, sweet. So that was number 9.
If we give you a tree and then we just say, oh look, every like there's no cycles, is that sufficient to say it's a tree?
As long as it's connected and no cycles. Yes.
Right. Okay.
If it's disconnected, then it wouldn't count as a tree. But yeah, that would totally convince me. Okay, let's do another problem. I think I'm going to change gears again. Let's go to number 14. Jumping around different parts of the semester here. Just want to make sure that by the time I'm done with the review, I've covered at least a lot of the topics. So number 14, so jumping ahead on the sheet. This one is another word problem that is a nice application. It says that an arm wrestler is the champion for 75 hours. So the arm wrestler is a champion for 75 hours. He had at least one match per hour, but no more than 125 total matches. Okay, show that he had exactly 24 matches in some stretch of consecutive hours. So I'm paraphrasing it a little bit from how I actually typed it out, but that's basically the question. Okay, back over here. So let's just read it again. The arm wrestler is champion for 75 hours. There was at least one match per hour, but no more than 125 total matches. To show that there was some stretch of hours that he must have had exactly 24 matches. So, what topic does this have anything to do with? Does it look familiar to anybody?
Pigeonhole.
Yeah, we've seen examples similar to this that were involving the pigeonhole principle, and that is a good starting point. Actually, if you just write this down on your paper, guys, I'm going to give you a couple of points for knowing that, right? Even if you don't do the rest of the problem. So try to get yourself partial credit by telling me as much that you know, especially something like this where you know what the technique is. That can be a really big help. So it really is a proof that we have a template for already. We've done these before. Of course, the numbers here, the numbers are different, but how you're going to like set up the notation and how it gets written up is basically going to be more or less the same for all of these kind of problems. So there were some of these in the homework. I know I put one on the first midterm. So it's definitely a good thing to make sure you can do. So what would you want me to do to kind of start my write-up here?
Sorry, what does being a champion for 75 hours mean exactly?
It just means he was doing arm wrestling for 75 hours in total.
Oh, I see.
This didn't go on for, you know, an indefinite amount of time. If this went on for an indefinite amount of time, then it might be hard to pin down like that there was a finite interval of time when he had exactly 24 matches. So, or at least a stretch of consecutive hours. What would be a good way to set this up?
Sequence.
I'm going to make sequences. I need notation for those sequences. But what is the notation that I might want to have? I think when I did these examples with you earlier in the semester, I used A sub I to denote the number of whatever it was, whether it was hours of television, whether it was the number of fish that were caught on the vacation. Here it would be the number of matches, the arm wrestling matches, right? So let A sub I be the number of matches during the first I hours. It's always, and that's not just during the ith hour, it's cumulatively during the first I hours. You have to write this correctly on your paper if I ask one of these. If you get sloppy and you just say, oh, A sub I is the number of matches in the ith hour, I would probably say, no, that's not what it's not, your proof isn't going to work that way. And then it's going to be hard for the rest of it to make sense. So be sure you get this thing denoted correctly. I could be, 1, 2, 3, ... I guess up to 75. So he's only doing this for 75 hours. But those would be the values of I. Now we are given that there was at least one match per hour. What does that tell you about these A sub I's?
They're an increasing.
They're definitely increasing because this is a cumulative effect, right? The number of matches in the first hour is obviously not as many as in the first 2 hours, which is not as many as the first 3 hours. But the thing is, it's actually strictly increasing because the AIs grow at least by 1 every hour. So note that A1 is strictly less than A2, which is strictly less than A3, all the way up to A75. Okay. So no two of those numbers are the same, but we would like to prove that somehow there's some interval of time between AI and AJ, 2 different time frames that has exactly a difference of 24. Right. By the way, obviously A1 is at least 1 because he's doing at least 1 match even in the first hour, and he has no more than a total of 125 matches. So even after 75 hours, he would have done it at most 125 times. Okay? So any thoughts on what I want to do? Do you remember what the next step of the argument is once we get this first? I know you were giving me a suggestion earlier, Gene. Here's one chain of inequalities. What do I need to do?
At 24.
Yeah, I need to make another chain of inequalities, and I want to do it in such a way that this 24 comes into it, because I don't see that really in anything we have so far. So we can just add 24. Sometimes you can just do this without even fully seeing the rest of the proof come together yet, but just adding 24 to everything would still preserve this inequality or this chain of inequalities, some of which are strict, most of which are actually strict. So if we now look at all of the numbers that are in the center of this collection of both of these chains, how many numbers is that? There's 75 on the first line, and another 75 on the second line. So we have 150 values that are between, well, the smallest that any of them could be is 1, and the largest that any of them could be is 149. So between 1 and 149, and these are integer values, and because they're integer values, then you have basically 149 boxes and 150 values. When you're using this pigeonhole principle, guys, a really, really good thing to check yourself on is, did you tell me what the boxes are? Did you tell me what the objects are? And did you tell me how to put those objects into the boxes? If you do that, right, then I can fully understand how you're applying the principle. If you just, at this point, if you just say, by the pigeonhole principle, we're done, that's too fast, right? So you have to try to write a little bit more down. I'm going to erase the question because I think we all have it written down now. So I'm going to come over here and write just a little bit more. So we can label 149 boxes from 1 to 149. So we can do that and then place each of the 150 numbers into the box with its value on it. I just like to really try to do a good job on this, okay? Now we can say, by the pigeonhole principle, by PP, there are 2 numbers in the same box. And we can even, we don't know what numbers they are, but we can give them notation. We could say A sub M is equal to, now here's the thing, none of the numbers on the first line can be the same as each other because these are strict inequalities. So this A sub M would have to agree with something from the second line, which could be A sub N plus 24. And this is for some M and N, which are in the range from 1 to 75. Guys, I'm kind of a stickler about quantifying your notation. So if I just see an M and an N show up and there's nothing written about what they are, then that would bother me. Right, I want to know, oh, M and N are integers that are between 1 and 75. They are subscripts that are coinciding with the terms over here. So that would be a good thing to do. So A sub M minus A sub N is 24. And the wrestler had exactly 24 matches, which is what we were trying to prove, exactly 24 matches during hours n plus 1, n plus 2, ... up to hour M. I think it should be clear that that M is bigger than N because AM minus AN is a positive value. What do you guys think? Does that make sense? That's a classic example of a pigeonhole principle problem, but there are others that you should look at. I remember there was the problem in the group work about my basketball games with Steph Curry. That's a nice example of proving that you must have like a consecutive number of things in a row but you have to know how to build your boxes and your objects for that. So definitely look at some of those other examples too, but we've seen this one a few times. It's just been a while. I wanted to practice it with you again. Let's do another problem. Everybody hanging in there? Do we need a break or we're doing okay?
Yeah, okay.
So far, so good. I'm only gonna go another like 45 minutes or so. And then whatever I'm not done with, I guess that was 14. Whatever I'm not done with, I'll have to save. By the way, number 3, I'm gonna cross number 3 off. That was actually the video that you're doing for the homework, number 14. So I didn't realize that I had actually put it in the review session, but that one you guys will be doing. Some of you have already turned in the homework, but that one we don't need to do together because you're going to watch that one when you submit your homework for tonight. Is it tonight? Yeah, tonight. Tonight there is homework due, believe it or not. Okay. Yes, I won't do that one. I think I'm gonna do number 16 next. Play with 16 for a minute. This one says find a recurrence relation. So go back to recurrence relation again for the number of ways A sub n to lay out a walkway of n tiles if the tiles are red, green, or yellow, so that no 3 red tiles are adjacent to each other, right? So no 3 red tiles are adjacent. Like that. Make sure this is totally in view here. Okay, find a recurrence relation for the number of ways A sub n to lay out a walkway of n tiles if the tiles could be red or green or yellow, and we cannot have 3 reds in a row. When you look at this question on the surface of it, it may look like it has to do with colorings because we're looking at the colors of these tiles. But this is actually not really about colorings as much as it is just a classic recurrence relations problem. This could be rephrased, right? This could be rephrased without talking about colors at all. This could be strings of 0s, 1s, and 2s, such that you do not have 3 zeros in a row. And it would be the exact same question. So sometimes the same problem can be sort of camouflaged in a slightly different way by just sort of setting up the wording differently or the physical nature of it a little bit differently. But yeah, this is no different than ternary strings that don't have 3 consecutive zeros. So what do you guys suggest that I do for the solution here as to how I should maybe start off?
Well, there's 2 easy cases, right? If you
Okay, let me
start
stop you right there, Hamza. So you said cases. That's
Yeah.
exactly what I would be thinking about. There are different types of acceptable strings here, and it would be nice to list out cases for what strings we could have. So we have cases of strings that we are going to look at, or that we are going to be counting. And you said, Hamza, you said there's 2 that are easy?
Yeah, because if you start with green or yellow, then it's just the recurrence relation on n minus 1.
Okay, so if I start my string with, and some people like to do it at the beginning and some like to do it at the end. I kind of like to put it at the beginning. Assuming that I start with a green string, then I obviously don't have 3 consecutive red tiles yet. And my issue of red tiles will be sort of transferred to the n minus 1 slots that we have. So there are A sub n minus 1 ways to finish this tiling. Right, so you could explain that like so, and same thing on the second case, if I started with a yellow one. There would be n minus 1 ways to finish that tiling. Okay, so that's 2 of the cases. Now, what else would we want to make a case for, do you think? We're doing number 16 right here. So the only other possibility is that we start with a red. So can I just do the red, can I handle red the same way that I handled the green and the yellow? Not so much, because we have this condition that no 3 red tiles can be adjacent. If I start with a red, and if I tried to just put n minus 1 here, the problem is that I could have some strings here that don't have 3 consecutive reds, but if they happen to start with 2 reds, maybe it's something like that. If they happen to start with 2 reds, this is a string we would have wanted to count until we put the red in the front. And then we would have 3 consecutive reds, and we're like, oh no, we can't count that one. So we really cannot just write down red as the first tile, because we have to be careful that we don't end up with 3 reds in a row. So what might we need to do here?
You can do like a red, green.
Okay, we could imagine that we had the red tile there, but then it followed up with green. At this point, it kind of resets itself, and the no 3 consecutive tiles thing can be applied to the n minus 2 slots that are coming after that. So on this one, I'm just going to use a ditto symbol here, guys, and write a sub n minus 2 ways to finish this tiling. All right, so that would certainly be fine. And the other thing we need to make sure of is that every case has been, so you want to make sure that the cases don't overlap. So there should be no string, that would fit the form of more than one of these. And also that every acceptable string is represented here somewhere. So I could have the red, green, what else could I have?
Red, yellow.
Red and yellow. And then we would get another n minus 2, and this is a sub n minus 2 ways to finish that tiling. Okay, anything else we would need to have?
The red, green case.
Okay, we could have 2 reds, which is not 3, right? We could have 2 reds and then switch to either the green or the yellow after that. So let me move this over here just a little bit. So I could have red, green, and then after that we would have a sub n minus 3 ways to finish. My ditto symbol again. And then we could also have red, yellow, which is also going to leave me with n minus 3 spaces, and we can finish in a sub n minus 3 ways. Okay, anything else we need to have? I think the only strings that are not represented in these 6 cases would be the ones that start with red, and we don't want those. No 3 red tiles are supposed to be adjacent. So I believe this is a comprehensive list of non-overlapping cases, and we can now just use the addition principle. By the addition principle, a sub n is the sum of all of these. So that would be 2 a sub n minus 1 plus 2 a sub n minus 2 plus 2 a sub n minus 3. It would be something like that. When I'm writing down a recurrence relation like this, technically that's the whole thing. But oftentimes there's going to be something else I want to ask you, which is, what if I asked you to find, this is actually in the question as well as a follow-up, find A7. So how many strings of 7 tiles could we have that don't have 3 consecutive reds? So what else would we probably want to figure out about the recurrence relation in order to be able to do the second question?
The initial conditions.
Yeah, the initial conditions really should be examined pretty much right along with the recurrence relation itself. So let's see about the initial conditions. And by the way, if we're talking about a walkway or any physical problem, please do not start with A0. A0 would be a walkway of 0 tiles. And you could get people disagreeing about what A0 is. Oh, there's no ways to tile no tiles, so A0 should be 0. But then somebody else might say, oh, but it's kind of like 0 factorial. That's not equal to 0 either. That's equal to 1. You know, and you can say, well, there is one way to tile an empty walkway, which is to do nothing. Well, does that count as one way of doing it? And so you don't want to get in the confusion of all that. So try not to use A0, guys. I have seen people, even on the midterm about this, they were doing that. So let's take physical problems only that make sense. Okay, so what about a walkway of length 1? We only have 1 tile. How many ways would there be to make that walkway? 3, right? What are the 3 ways?
The red, the green, the yellow.
Yeah, just use a red tile, just use a green tile, or just use a yellow tile. Absolutely. Yeah, I like it. What about if my walkway has 2 tiles? Doesn't hurt to give yourself a little visual here. You have 2 tiles. How many ways could we color that?
You have 3 choices for each, so 3 squared.
There's no constraint, right? Because the 3 consecutive reds isn't going to come into play yet. So it is just, 3 choices for the first color, 3 choices for the second color. That's just 9. Okay. And anybody want to try the A3 value? Is it just 3 choices, 3 choices, 3 choices? That would be 27.
26.
But the right answer is 26. Exactly. Why is that, Kevin?
It's like 3 to the power of 3 is 27, but like you gotta take out where the 3 tiles are red, so.
Exactly. There's one of these 27 tilings that is red, red, red. We have to remove that one. And so now we have 26 that would be acceptable. Yeah, so these would be the initial conditions. By the way, you notice that the number of initial conditions that I gave here matches the order of the recurrence relation. This is a 3rd order recurrence relation, so I would want to have 3 initial values. And now we can solve for A4, A5, A6, and A7. I won't spend too much time on this, but if you work out, somewhere I have the answers. I think I'll just tell you what these are, and then you guys can do the actual calculation later. It's not a big deal, but the number did come out kind of big. So A4 is already 76. If you add these up, you get 38, but then you have to multiply by 2 because there's a factor of 2 that comes out, so that's 76. And then for A5, I got 222. And then for A6, I got 648. And then finally for A7, I got 1,892. So don't get too worried about something like that. I mean, if you made a mistake with the number there, I'd probably not be too worried about it in terms of grading, as long as I know that you know what you're doing. The main thing is don't take the A7 and break it down using 6, 5, and 4, and then having to break down the 6 into 5, 4, 3, and all that. That gets messier than just doing this. So it's best to just work uphill with your calculations. I think you will be much happier with that. Okay. Sweet. So that's number 16. Are there any questions on that one? Does it seem okay? Okay. I have one that I think might challenge us a little bit. Let's do number 10. Gotta go backwards on the sheet a little bit here, guys. Try number 10. So number 10 says the following. How many 16 bead necklaces can be made using red, green, and blue beads? So 16 bead necklaces. We're going to use red, green, and blue beads if the necklace must have at least one red bead, at least one blue bead, or the beads must alternate between two of the colors. Oh, this is kind of crazy. So I got that all written down, and this one's going to take a little bit of work. Let's see if we can figure it out. One thing that's going to make this a little bit challenging is the 16 is pretty big. And so if I think about necklaces, what kind of topic are we kind of inclined to think about here? Counting necklaces. Have we talked about necklaces anytime this semester? I think so. What was the context of it? Counting non-equivalent colorings of this object, yeah? And what's the tool that we learned that's going to be really important, that is almost for sure going to be on this test, that we would use for that? The Burnside theorem that we learned on just this past week, right? So yeah, I think we're going to want to use Burnside's theorem. And again, if you just write that down, if this was actually on the test and you just wrote that down, I'd be able to give you some points for recognizing that that's what this question is about and that that's the tool we need to use. But this is a Burnside's theorem with a twist, because it's not just saying how many 16 bead necklaces there are. There's actually constraints that we also have here. So what I'm going to recommend is that we maybe solve the problem without constraints first and then subtract violations. So what we could do is we could just say, what is the number of non-equivalent necklaces using 3 colors? And our notation for this was the N of G and C that we saw in the Burnside's theorem. And what we do here to find the number of non-equivalent necklaces is we create this fraction. And so this is where you have to remember the Burnside's theorem. Maybe I should write it out in the general notation first. We do a summation over every symmetry of the necklace. So that's F in the group of symmetries G of the size of C of F. C of F, those were the colorings that are fixed by F, and then we divide by the size of the group. If it helps you, we can draw the 16 bead necklace out. You know, it's possible to do this without drawing the picture, and you can see it's going to be a lot of beads. But you might find it's helpful to draw this. So I will not be upset with you for drawing this picture, but I've lost track of counting the beads. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, something like that. And it's just this necklace going like this. Okay. Okay, so there's my necklace, and this is just forming a cycle graph of C16. It's actually what we have there. So far, so good? Okay, great. So does anybody know what the size of this group is going to be? The symmetries of this 16 gon? I think we know that if there's a square, we had the dihedral group, which had 8 symmetries, right? There were 4 rotations and 4 reflections. But for a 16 gon, what would be the number of rotations and reflections?
Could be 32, right?
I have 1 vote for 32. Does that seem okay? Yeah, so this thing has, you know, a 1/16 rotation, a 2/16 rotation, a 3/16 rotation, all the way around until you've rotated the whole entire 16/16. That's 16 rotations. Right, and we could even denote them as rows of 16 and rows of 16 squared and so on up to rows of 16 to the 15th, and then the identity element would be like a rotation all the way around, or in other words, a rotation of 0. So there's 16 of those, and then the reflections, you might remember with the square there were 2 types of reflections. There were the ones going through opposite vertices diagonally, and then they're the ones going through the center of 2 opposite sides. We have that here too. Okay, we have that here too. So we're going to have 16 reflections. We don't obviously have any notation for these, but we could call them tau 1, tau 2, and ... up to tau 16. It's just a dihedral group with 16 symmetries of reflections and 16 symmetries of rotation. So 32 elements looks good to me. Okay, let's see if we can figure out these C of F's. I usually like to start with the identity symmetry first, just to get warmed up. It's the easiest one to think about. If we were just coloring this necklace with the red, blue, and green beads, and we wanted to know which colorings would be fixed by the identity coloring, identity symmetry, the answer would be all colorings. Doesn't matter how you color the necklace, if you're just going to pick it up and set it right back down again in the same spot, it doesn't matter what colors you used, that coloring will be fixed by that action. So that's, I guess my question is, how many ways would there be to color these vertices?
16.
3 choices, 3 choices, 3 choices, 3 choices. We can reuse the red, the green, the blue as much as we want, at least for now. In a minute, we're going to put a constraint in this, but for now, we can do anything we want, guys. So that first term in the numerator would just be 3 to the 16th. Okay. What about doing a 1/16 rotation? How many colorings could we make that would stay unchanged by rotating this thing just 1 click to the right? So you pick a color, let's say for the top vertex, let's say you pick green, right? Once you've done that, now you're gonna rotate this by 1/16. So if I want this, if I want to think about where this green color goes, it's going to go over here. Right? The green is going to move there, which means that in order for it to be unchanged, that vertex had better have been green to begin with. Right? But then that green is going to end up shifting to here. And so in order for this vertex to, for this vertex to stay the same, it will have to have been green to begin with as well. And do you see what's going to happen?
They're all gonna be.
They're all going to have to be green. So whatever color I chose at the beginning here is actually the color I would have to use for the entire necklace. And I only have 3 colors. So that means I only have 3 choices for that term. Now, if I do this one by one, I'm going to end up with 32 terms in the numerator here. Because there's 32 different symmetries. Is it fair to say that all of the rotations would have this same 3 in them? So what about a 2/16 rotation? So let me start over. If I do sort of the row 16 squared, if I do a 2/16 rotation, then this green would actually move over to here, right? And if it moves over here, then this vertex needed to be green to begin with, to be compatible with that one. And actually what happens is the greens would have to be in every other position, you would have to have green. But what about the opposite ones? Does this one have to be green as well?
Those could be anything, right?
Those could be anything. I could put my, what did I have here? I could decide to do these red. And then I would have to make all the rest of them red as well. But that is actually true. I don't have to make them all the same color anymore. This is because I used 16. Oh my gosh. It's a tricky number. If I'd used like some prime number, like 11 or something, 11 beads, it'd be a lot easier. But in this case, the row 16 squared actually gives me 3 squared ways of coloring it. I can do green, red, green, red, green, red, or I could do green, 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 or I could do red, green, red, green, red, green. Or I could do the same combinations with the blue. So 3 choices, basically you have 3 choices here and 3 choices here, leading to a total of 9. Okay. Now, what about 3/16? Row 16 cubed. How many necklaces would we be able to have, or how many colorings of this figure would be unchanged by a 3/16 rotation? If I kind of start over again, okay, so go back to the top of the necklace. Let's say I go green again, right? Now, 3/16 would put green here. And then 3 more 16ths would put green there, and then there, and then there, and then there, and then 3 more 16ths puts it here, and it's wrapping around, guys. It's wrapping around. It's not on top of the greens that we had before. 1, 2, 3. We end up actually with only a uniform color around all the vertices. The next term is also a 3. Right? And then we could do the 4/16. What do you imagine for the 4/16? That's really a 1/4 rotation. Anybody have a guess as to what that term will be in the numerator? 3 to the power of, I don't think it's 2. So if I start with green here and I rotate 4/16 around, I go there. And then 1, 2, 3, 4/16 is here. 1, 2, 3, 4/16 is here. And then 1, 2, 3, I'm back to there again. So I only colored 4 of the vertices with the green, and I still have a lot more vertices I can choose.
Would be 3 to the 4 because you get 4 choices, right?
Yeah, that's right. You can choose these first 4 vertices in any combination you want, and then when you rotate by 1/4 of the way around, that will color the next 4, and then the next 4, and then the last 4, right? So it is actually 3 to the 4th. Yeah. Okay, what about a 5/16 rotation? Actually, believe it or not, guys, there's a fair bit of number theory on this. It has to do with like how many common factors your rotation amount is relative with 16. How many common factors of 2? Right, so 5 is relatively prime to 16. And if you start coloring every 5th vertex around this necklace, you will never repeat the same vertex again until they've all been hit. That means that's a 3 again. Okay, and then the next one is 6/16 of the way around, which is going to turn out to be the same as doing 2/16. So this is going to be 3 squared again. And then 7/16 will be 3 again, because again, 7 is relatively prime to 16. Every other one is just 3. And then 8/16, this is rotating it halfway around. So you have the 16 bead necklace and you're rotating it exactly 180 degrees around. So the colors that you use on the top half are going to dictate the colors that you use on the bottom half, but the top half is already 3 to the 8th, like so. So that would be 8/16, and I need a much bigger numerator than I've got, so I got to keep going here on top. Then we go 9/16, that's just going to be 3 again. 10/16 is going to be back to 3 squared. 11/16 is 3. 12/16 will actually be 3 to the 4th. That's just a counterclockwise rotation by 4/16. So that's 3 to the 4th. 13/16 gives me 3. 14/16 is 3 squared. 15/16 is 3. And that's it for the rotations. That's only the rotations. Ay.
Do you just put the GCD in the exponent? Is that what you're doing?
Yeah,
Okay.
exactly. You could just say it's 3 raised to the power of the GCD of the rotation amount of I with 16. Definitely. Yeah, so that could be simplified. And actually, if you figure this out and you realize you don't want to write out all these terms, you could just figure out, well, how many factors of 3 do we need? How many factors of 3 squared do we need? And how many 3 cubes 3 to the 4ths do we need? And so on. Okay. But anyway, I've already written them all out here, so I'll go ahead and leave it at that. Now, I still have to do the reflections. The reflections. Does anybody have any thoughts about the reflections? How many of these vertices could I color at will? And then the reflection would force me to color the others. Any thoughts about that? There's 16 reflections. If you need to, just think about a square again, right? There's the reflection that goes like that, and then there's also this type of reflection. They're actually not the same. If we had this one, we would have, 3 choices, 3 choices, and 3 choices. That would be 27. But if we had this square, we would only have 3 choices on one side, and then the mirror image would be forced to be compatible on the opposite side. So it's 3 squared versus 3 cubed. Any thoughts about if we jack that up to a 16 gon, what would be the analogous thing? And half of these reflections are actually going through the two opposite vertices, and half of them are cutting through the center of an edge. What's the total number of reflections? 16. So I claim here that 8 of them will be of one type, and the other 8 of them will be of the other type. And I'm going to actually combine these together. 8 of them are going to be of this type. Now, when it's of this type here, guys, then that means that exactly half of the vertices are on one side and have to be colored. The other half are on the other side and are forced to be the same color. So if there's 16 beads, we're coloring half of them. That would be 8 of them on the left half with whatever colors we want. Okay? But then there's 8 other reflections where we go through diagonally opposite vertices. And notice that that gave us a different number of choices. It was actually 3 cubed here. What do you suppose for a 16 bead necklace it's going to be? 3 to how many powers do you expect I'll have? I mean, we could draw the whole figure out, but so that's half of it, right? So here's 1, 2, 3, 4, 5, 6, 7. Nope, that's not half of it. Sorry. I should draw this a little bit better. Let me try to do a little better job. So I'll put the 4 corners here. And then there's 2, in the center of those, there's 1, and then there's another one in the center of each of those. So I'm just redrawing my picture. Now I should have 16 vertices there, and here's a diagonal, right? And the question is going to be, so I have 3 choices here, 3 here, 3 here, 3 here, 3, 3, 3, 3, and even 3 there, but then I don't have choices on those. How many 3s is that? 9. It's 3 to the 9. Does that make sense? It's just like here, half of the reflections gave me 3 squared, and half of them gave me 3 cubed. It's because when the reflection goes through 2 of the vertices, then both of those vertices have 3 independent choices. Here, each vertex sort of has a partner on the opposite side. So you only get half of the vertices with 3 choices. Here you get 1 extra one, if you think of it that way. This works great for the even-sided figures, not so much for the odd-sided figures. For the odd-sided figures, and there's one in the homework, I think for tonight you have a 7-sided figure. For the odd-sided figure, these reflections will go through a vertex on one side, let's use 5 for example, and through the opposite edge on the other side. So here the reflections are going through a vertex and an edge. So it's a little different with odd-shaped figures when you're doing reflections. But anyway, for even-sided figures, it's usually a little bit harder, and you have to break the reflections into 2 types, like what we did here. So what I have so far on the board, guys, is that's the number, that whole thing with the 32 on the bottom of it, that is the number of 16 bead necklaces that we can make using red, green, and blue beads. I haven't even gotten into the constraints yet. So we have to subtract violations now. So this is the total. That's the total, and now I'm going to subtract violations. Oh my gosh. Let's talk about the violations. So I'm going to subtract violations from that total. What kind of violations can I have? Let's see. A violation would be if I don't have at least 1 red bead, right? So one type of violation would be this A is the set of necklaces without a red bead. Maybe I can say it that way. So necklaces that do not have a red bead, that would violate the at least one red bead clause. And then there's at least one blue bead. So necklaces without a blue bead, that would be another set. And then C would be the ones that alternate. Necklaces must have at least one red bead, at least one blue bead. Wait a second. Or they alternate. Oh, yeah, this is. Oh my gosh. Yeah, Kevin.
Can we say that for the C violation, can we say that like if the same colors are glued together?
I don't think that's actually what we want to say. I think the third scenario is necklaces that oscillate between two colors, but I have a little problem here, which is I've created the sets A and B as violations, but then C is not a violation. C is actually what I want. That is an allowed option, which is that the beads alternate between two of the colors. So I need to actually change this. I'm going to go back to sets A and B, guys, and I'm going to make set A the necklaces with at least one red bead, and set B is necklaces with at least one blue bead, and C is necklaces with oscillation between two colors. I'm going to actually, instead of making these into violations, I'm sorry, I'm not really thinking of this as violations here. I am looking for the sizes of these sets, is basically my point. So let me see if I can explain this. So I am looking not to subtract violations, but to just count this union. Necklaces with at least one red bead, or at least one blue bead, or which oscillate between the two colors. Yeah, that's actually what I want. And so we have our inclusion exclusion principle. So there's a little bit of that going on here too. I think I told you guys this was going to be a challenging one. I got a little carried away, but that's okay. As long as it's in the review session, I don't mind. So there's your expression. But if I want to figure out the size of A, here, then I'm actually asking how many necklaces would have at least one red bead. And to do that, we actually need to use the subtraction trick. So take the total number of necklaces, oh geez, which is this thing over here. Can I label this with star? I don't have a big enough board. It's going to be that star minus necklaces that do not have any red beads. And if they don't have any red beads, then that they would have only blue and green, and it would be the same formula except with twos instead of threes. Right? So instead of a star, let's not use a star. Let's use, let's call this thing f of 3. So f of 3 is this expression. In general, f of p would be p to the 16th plus p squared plus p plus blah, 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 right? So I'm going to think of A as being f of 3 minus f of 2. These would be all possible necklaces minus the necklaces that only use green and blue. Okay? And then for the size of B, which is the necklaces with at least one blue bead, I'm going to take all necklaces, which is f of 3, and I'm going to subtract those necklaces that only use red and green beads, and there would be f of 2 of those. Next, I'm going to count how many necklaces oscillate between two colors. That we should be able to just think about physically in our head. If I have a necklace that is 16 beads and it's oscillating between two colors, how many different necklaces do you think you could make?
3.
3 is the answer I have in my head as well. I can either oscillate red, blue, red, blue, red, blue, or I can oscillate red, green, red, green, red, green, or I can oscillate blue, green, blue, green, blue, green, and so on. That's it. So you just have those 3. Okay. Awesome. Now let's subtract violations. Oh boy. The violations. Let's see. A intersect B. That would be necklaces with at least one red bead and at least one blue bead. So how about we do this? Oh guys, you guys are gonna hate me. Let's do all necklaces. I'm going to subtract the necklaces that don't have any red beads. That would be f of 2. I'm then going to subtract the necklaces that don't have any blue beads. That would be f of 2. But then I have double subtracted the necklaces that don't have any red beads or any blue beads. And I need to add those back in. How many necklaces don't have any red beads and don't have any blue beads? Kind of a trick question.
Oh, just one? Because it's just one color?
It's just it's f of 1, which would just be 1. It would be the necklace of all greens. So we're doing a little mini inclusion exclusion right there within just that part with the brackets to just figure this out. Okay. I should have saved this one for the exam. What's that?
I said I would have cried.
Everybody would be crying. I'd be like, oh, I bet they're working on problem number 10. Let's see. What about A intersect C? Necklaces that have at least one red bead, but they do oscillate between two colors. How many of those necklaces would there be?
2? Because if we have to have at least one red bead, and we have 2 options for the other colors.
Right.
For the
So
other-
it's either red, blue, red, blue, red, blue, or it's red, green, red, green, red, green. If you were saying it has to have at least one red bead and it has to oscillate, that would be it. There's only 2, right? And then B intersect C would be necklaces that have at least one blue bead and which oscillate between 2 colors. How many of those would there be? Also 2, right? Because you have to use a blue bead and you have to oscillate. So it could be blue, green, blue, green, blue, green, blue, green, or it could be blue, red, blue, red, blue, red, blue, red. Exactly. Okay. And finally, we have to add the 3-way intersections. How many necklaces have at least one red bead and at least one blue bead and oscillate between the 2 colors?
1.
Only 1. Yeah, that's right. That would be only 1. And so there is your answer. Actually, it can be simplified a little bit. Like the f of 3 here cancels that f of 3. And then here we're subtracting f of 2, but here we're really adding f of 2. We can get rid of that. Here's another minus f of 2, and here's another plus f of 2. And then I have a plus 3 and plus 1 cancels with minus 4. right? And at this point, it's actually turning into just f of 3 minus 1. Interesting. So anyway, but we would not be getting a numerical answer for that because without a calculator, these big powers of 3 are going to be too difficult. I think I just did the hardest one on the sheet, which is that number 10. Got that one done today, which is probably for the best. Everybody okay with that? Oh yeah. All right, let's go to something else. Guess I'm gonna go for maybe another 25 minutes or so. So I made a mistake. I was supposed to go till 2, right? It's about 1:30. I do need to take a break before 2 at the latest because I've got to go somewhere and come back before 3. So we will not go too much longer, but I'd like to at least have half of these done so that I don't have to do too many extras tomorrow. So let's do something a little easier maybe. How about we just do number 11 while we're on it? Number 11 I think is a pretty easy one and won't take us as long. We'll feel like we're getting a little more progress. So prove combinatorially so give a combinatorial proof. And here it is, 2n choose n equals n choose 0 squared plus n choose 1 squared plus ... plus n choose n squared. We'll try this one. This one hopefully won't be quite so involved as that last one that we just did. By the way, though, guys, you should pretty much, sorry, quick, go back to the last question for a second. You should expect a Burnside theorem problem for sure on the test. Probably not 16 beads, but you could imagine I might pick a different number and I might ask you how many non-equivalent colorings, or I could throw a twist and instead of a necklace, I could give you a merry-go-round, which was something that was on the group work that we briefly looked at. I didn't have time to really go through that in detail. So take a look at that last group work that we passed out just on Thursday and make sure you can do these Burnside theorem problems. I might even have more than one of them for all I know, because I really like the theorem. It's a nice culminating result. And you see how I cleverly combine Burnside's theorem with the inclusion-exclusion principle here. That would be like, a really... I like to combine ideas sometimes, so should be definitely planning for something like that. Okay, anyway, I'll get off my soapbox about that right now. Let's take a look at this problem over here. Does anybody have an idea how to write out? This is usually in words. It takes a paragraph to explain it. But does anybody have a thought about either a story that we could create or just a setup of a counting problem that would sort of be viewed in 2 different ways? There's often many right answers here. There's as many as creative as you want to get, with what you're doing.
If you have n men and n women and you want to make a committee of n people, I guess. Is that...
Okay, let's start with that. Consider a group of n men and n women. The number of ways to make a committee of size n is, so on the one hand, it is just 2n choose n. So which is the left-hand side. Now, sometimes the way I set this up is I'll I'll actually have a paragraph to explain the left side, and then I'll have another paragraph to explain the right side. In this case, the left-hand side is so simple that it's actually directly associated to what we're counting. So we can just say that immediately. If we had, instead of men and women, if we had decided to do red balls and green balls, you have N red balls and N green balls, and I'd like to choose N of them. But if you did that, I would want you to be a little more clear. Are the balls distinct or identical? If I'm doing men and women, we can assume they're distinct. Like we tend to do that. They should be viewed as distinct. But for balls, if I wanted to tell a story about N red balls and N green balls, they should be N distinct red balls and N distinct green balls. So just to clarify that a little bit. But I like Hamza's idea of just using men and women and making a committee here. Okay, can somebody help me understand the right-hand side? Because it has to match up with the 2N choose N if we do this properly. Somebody besides Hamza. Hamza had the idea for the counting, but then I'd like to hear from somebody else to maybe explain how the right-hand side is going to give me the number of such committees.
I feel like the right-hand side is giving like cases in a way. Of,
Yeah. There are cases according to, and what would be the key thing that distinguishes the cases?
The addition principle.
Well, that's what we'll use. Once we have, there are cases according to something, and then once we write out all the cases, we will add them together by using the addition principle. That's going to come, you're thinking ahead, that's definitely going to be a big point at the end of this paragraph. But like, how do we actually get these terms? Does anybody see like how the N men and the N women are creating these terms over here?
Essentially picking a one man and one woman, but at the start we're choosing 0 men and 0 women.
Are we choosing 0 men and 0 women here?
Well, we know,
My
like,
committee has to have size N, right?
yeah, I
Sorry?
was going to say that, like, N choose 0 and N choose N are giving us the same number. So essentially we're choosing for the first one 0 women and then N men. And then the next case is we're choosing 1 woman and N minus 1 men and then so on.
Yeah, that's actually, thank you, Vivian, that's exactly right. So these are cases, as we were describing there, but the point is that you have to have a certain number of men and a certain number of women. So let's say these are cases according to the number, I'll call it K, of women chosen. So you're choosing K women out of the N women, and N minus K men chosen. And so there is a 2-step task that we're doing. So, and we should write down the tasks we're doing. So we have N choose K ways to choose the women, and N choose N minus K ways to choose the men. So we have N choose K ways to choose the women, and N choose N minus K ways to choose the men. And so now, by the multiplication principle, we have, well, it would be N choose K times N choose N minus K, which, by the way, is the same as N choose K squared, because remember that N choose N minus K is the same as N choose K. So there are n choose k squared ways to choose the committee. And now we just need to sum all the cases over what k could be. You could have no women, you could have one woman, you could have two women, or you could have all the way up to n women. So summing, this is the part Kevin was explaining the addition principle. So summing over k from k equals 0, 1, 2, dot, 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 up to n gives the right-hand side. That would give us at that point, that would give us the right-hand side. And that should wrap up the proof then. That should explain it pretty good at that point. What do you guys think? If instead of men and women, it was red balls and green balls, of course, you just put those words in those places and the whole proof would be exactly the same. Yeah. Yeah, so it's a little tricky because you're not choosing 0 women and 0 men. You have to use this n choose n minus k thing to make it make sense. Yeah. In total, you've chosen n people. K of them are women and n minus k of them are men. Yeah. I like that. Questions, comments, thoughts about any of that? Seems okay. All right, so that was number 11. I think I have time to do one more maybe. Let's see, I still have quite a bit to go here, but that's okay. We'll get there. I want to pick something that's a little different topic. Maybe let's do 17 for now. I think we can do that. And some of these are kind of repetitious, so I'm trying to not pick the same topic too many times. I want to keep practicing different things. So 17, this is certainly something good to remind ourselves about. Decide if the graphs are isomorphic, which I didn't really ask you much about on the, I guess there was one question on the second midterm about this, but there wasn't a whole lot. So the first graph is, I'm gonna provide a circle here and label 6 points around the circle. So A, B, C, D, E, F. So just 6 points around the edge of a circle. And then I'm simply going to draw in all of the opposite diagonals. I'm just going to make diagonals going all the way across. And then the second graph that we're going to compare this one with is going to be this graph here. 2 rows of vertices, each with 3 vertices in them. And then I'm actually filling out a graph that, in this case, I hope will maybe look a little bit familiar. I can label these vertices 1, 2, 3, 4, 5, and 6 like that. And does anybody recognize that second graph, by the way? What's that? Did you say it? No. I think I heard you say it. Maybe not. Okay, does somebody else want to try? What is this graph?
That's
K33.
Yeah, that's just K33. That is your complete bipartite graph. Yeah, so that's the complete bipartite graph. Okay, fantastic. So that's the question is, are these two graphs isomorphic or not? If they are, we should create a theta, which is the isomorphism between the two. Otherwise, we should find some structural difference between them that makes them incompatible. If I already know that one of my graphs is a bipartite graph, I could look at the other one and ask myself, is it also bipartite? right? So we could actually do the whole process that I like to do normally, where I circle the vertices and then I put diamonds around the ones that are adjacent to that. And you will very quickly see that it is bipartite. You can split up these vertices into two camps just like that. Also, I got a little bit ahead of myself. The two graphs, they should have the same number of edges. They should have the same degree sequence. Everything that we've studied should be the same. If one of them, I think we learned that this one's not planar. K33 is not planar. So then this one should be not planar. So everything should be compatible about these graphs. The fact that I've actually got the 6 vertices broken down now into 2 groups of 3 for both graphs is very helpful in terms of like if we were going to make an isomorphism. And I think you could pretty reasonably say that this is just K33 also. I've got 3 vertices that are not connected to each other, like F, B, and D. And I also have A, C, and E that are not connected to each other. And you could lay this graph back down. You could, if you wanted, you could even redraw it. Now you technically don't have to redraw the graph, but you could redraw this graph by kind of putting the 2 camps of vertices in the same configuration as to how this second graph was drawn. And you will see immediately that, yeah, I have to have the edge from A to B, from A to D, and from A to F, and then from C to B, from C to D, and C to F, and finally from E to B, and then E to D, and E to F. And that's every edge that you have. And so there is absolutely going to be a isomorphism here. So this is going to be a yes. And if you've drawn the second graph like so, I don't always recommend doing that, but if you have it already redrawn, then you literally can, you can make your theta just by matching them up directly, right? So theta of A should be 1, theta of B should be 6, theta of C should be 2, theta of D should be 5, theta of E would be 3, and theta of F would be 4. And that would do it. That would absolutely do it. Yeah, so that's pretty cool. That's pretty straightforward. Is everybody good with that? I was just looking at the second one that I have. I have a part B to this. I must have been having a really slow day. Let me show you what I put for part B. You guys are going to wish I saved this for the midterm or for the final. So there's one more example of this. This should give. Let's see how we do with this. So I've got this picture here. I got 3 vertical segments going down like that. And then across the top and across the bottom. And then I've got the curvy edge joining the top and bottom like that. And then my second graph is this one here. Okay, so I'm kind of putting this in like so. I'm gonna go across the top, go across the bottom, all those edges, and then the side like that, and then the center also, and then I'm gonna go diagonally across like this. Okay, so those are my 2 pictures. And I'm asking, are those graphs isomorphic or not? They're not. Why not?
The vertices different or like
How
the
so?
numbers
Yeah.
or the size.
I think if I put this on the exam, you guys are like really happy with me. I didn't realize I made a problem that was like this. I don't think we've had one like this before. They don't even have the same number of vertices. So that's like the first thing you check. If you don't have two graphs with the same number of vertices, then there can't even be a bijection between them, let alone a edge preserving isomorphism. So yeah, this was probably too easy. But I happen to have it on my handout. Yeah, it's always good to just make sure people are thinking things through a little bit. So that's 17. You want to do one more? That one was faster than I thought. Or do you want to call it a day? How many have I done? 1, 2, 3, 4, 5, 6, 7, 8, 9. I should do one more so that I have 10 things done. Let's do number 19. Although I'm gonna have to draw another graph to do number 19, but that's okay. So keep practicing these isomorphisms a little bit. This was kind of too weak of an example, but there's lots of good examples back in the homework and certainly in the midterm resource folders and stuff like that. You could go back and review that. So number 19 is just going to ask you whether this graph is planar. So is this a planar graph? We haven't talked about planar graphs today, so let me do it right here. I'm gonna lay some points out around a circle again, kind of. So something like that. Let me actually label the vertices before I draw any further edges into it. So A, B, C, D, E, F, G, H, and I. And I've already made a couple of mistakes here. There should not be an edge between E and F, and there should not be an edge between B and C. So I added edges that I shouldn't have added there. And now I'm going to start adding some other edges into the middle of the graph. So A should be connected also to D, and to E, and to G. So that's what A is connected with. B should also have an edge to F and to E. So I'll add that one. C should also be connected to F. I'll add that one. Let's see. I think I'm good with D already. E should be connected to H as well. And then F should be connected to I. And I actually think that's everything now. That should be my graph at this point. So I'll give everybody a chance to finish drawing it before we analyze it. And we're gonna try to figure out whether this is planar or not. Which just means, can I redraw this graph so that there are no crossing edges? There's enough edges there that it's maybe not obvious. I'll just remind you that as long as it's a connected graph, there is a edge requirement that has to be satisfied. So you probably remember, so if G is planar and connected, then does anybody remember the inequality for the number of edges? 3n minus 6, actually. Yeah, minus 6. You're thinking of the one if there's also no 3 cycle in the graph,
Yeah.
then E is less than or equal to 2n minus 4. Yeah. So there are some other inequalities that we have looked at. Oops, there are some what I'll call better inequalities that are sometimes available if the graph doesn't have 3 cycles or possibly 3 cycles and 4 cycles and so on. Are we allowed to use any of the better inequalities on this graph? to use this one, for example, that there would need to be no 3 cycles. Does this graph have any 3 cycles? It does, unfortunately. I see some triangles, right? So like you have ADE as a nice triangle there. So you're not going to be able to use the 2n minus 4 inequality for sure. Okay, so but let's just see what happens if I use this edge inequality. So E and N are the values we need to find. I'll start with N. I think I can see 1, 2, 3, 4, 5, 6, 7, 8. I see 9 vertices there. So I've got 9 vertices, and then to figure out how many edges I have, I think I'm going to use the handshaking theorem. So the number of edges is the sum of the degrees of the vertices and then divided by 2. So vertex A has 5, B is 3, C is 2, D is 3, E is 4, F is 4, G is 3, H is 3, and I is 3. 2, 3, 4, 5, 6, 7, 8, 9. Yep, I've got 9 terms there. And let's add that all up. 8, 10, that's 10 plus 11 plus 9, that would be 30. Divided by 2, it should be 15, guys. If I've not made a mistake, it should be 15. Well, 3n minus 6 is 21, which is way more than 15. There is no contradiction here. It doesn't mean that the graph would have to be planar. It just means we cannot say that it's non-planar by using the contrapositive of this. We have to basically figure out another way to do this. One thing we could do is we could draw this graph. We could try to redraw the graph with no crossing edges. But if we're taking a final exam and we're kind of limited on time, we're going to have to not spend too much time on that. It could take a lot of time. It's kind of an unsolved question. It's just like, well, how do you do this? How do you redraw it? You could spend 30 seconds if the first thing you find works, or you could be kind of hunting and hunting and hunting for a way to do it, and it might never come to fruition. So to be a little careful about getting, this is the type of problem that somebody could get hung up on for longer than you should. It's only going to be worth less than 10% of the final. You don't want to be spending like 30 minutes on it. So give it a try. And you can write down what you know, what calculations you've done, maybe if you've tried to redraw it. But if you're not getting a confident answer fairly quickly, I would set that aside and come back to it later. Yeah. Any thoughts here, guys? What I could do to make it an easier problem would be, instead of saying, is it planar? I could write a better question for a test situation, and I could say, show that this is not planar. If I do it that way, then at least you're not like fumbling around going down the rabbit hole the wrong direction. At least you know what you're supposed to be doing. It turns out this one is not planar. And so what kind of tools, other than this, which didn't work, what other tools do we have that would be convincing reasons why we would know that a graph is not planar? Anybody remember any big theorems?
If there's a K33 embedded in it?
Oh, okay. So if there's a K33 or if there's a K5 inside of the graph, then by Kuratowski's theorem, so that's the name of the result, Kuratowski's theorem. So I'm just putting this on the board so that you guys hopefully will review this one. Kuratowski's theorem, this is the one that says that a graph is not planar if and only if it contains a subgraph that is homeomorphic to either K5 or K33. Now, oh, I just erased the degrees of these vertices. But if you look at the degrees of these vertices again, it was 5, 3, 2, 3, 4, 4, 3, 3, 3. K5 would have to have 5 vertices all of degree 4. And I don't see enough degrees there for that. I see there could be 3 vertices potentially that would have a big enough degree that they would connect to everything else. But the K5 is looking a little unlikely based on the low degrees that we see. K33, on the other hand, would require, well, 6 vertices of degree 3. Well, we actually have 8 vertices that have degree 3 or more here. Remember, you're looking at a subgraph, so you might not be using all of the degrees that are showing up here. So K33 actually seems possible, that it might actually be possible. So can we find sort of 2 groups of 3 vertices here? That means we're not going to use all 9 vertices. We're only going to use 6 of them. We're only going to use 6 of them. And I'm going to try to put them into camps here. And let's just see what we could maybe come up with. Like I could put H in the same camp with A. And notice that both A and H, they both are connected to I. So that would mean I would kind of go in the other camp. Right? And notice that they're also both connected to G as well. So G could go into that other camp. And, oh, look at this. Vertex F is not connected to A or to H, right? And it is connected to G and I. So I'm feeling like I'm getting pretty close to having the bipartition already figured out. I need one more diamond. Which one?
E.
E. So if I go with E, E is connected to A and to H, but not to I and not to G. But there is one problem, which is that I'm going to go ahead and draw you guys a picture. So I've got A, and I've got H, and I've got F, and I've got down here on the second group, I've got I and G and E. And let's just draw the edges that go with those 6 vertices. So A is connected to I and to G and to E, and H is connected to I and to G and to E. And then if I look at F, F is connected to I and to G, but F is not connected to E. So it's almost a subgraph that is isomorphic to K33. We almost have the K33 there, but we don't have an edge from F to E. Does that mean this whole thing doesn't work? Oh, it's after 2 already. Actually, it still does work because even though there's not an edge from F to E, there is an edge from F to C, and then from C to D, and then from D to E. If you kind of look here, you can get from F to E by using the C, the D, and the E. This is homeomorphic to the K33. I've added a couple more vertices and made these dots along that edge, but this is not planar the way I've drawn it. And whether those dots are there or not doesn't affect that, right? Because you can bend these edges as much as you want. Just putting a couple of dots somewhere doesn't change the property of whether the edges have to cross or not. So you can certainly do that. And so the answer is this is not planar because there is a subgraph that is homeomorphic to K33. And we can list the two, what you should do in your solution. I don't think I'm going to take the time to write it up right now because I do want to get going, but you can just draw what the two camps are. And that would be more than adequate for me. Yeah, if you're not sure how to do it, at least just write down what Kuratowski's theorem says, write the name and tell me what the theorem says. I can give you credit for that. If you attempt to make a subgraph, show me that too. Maybe you didn't remember the homeomorphic part and this was all you had. Well, I would give you a lot of credit for looking for the right thing in your picture and almost getting there, right? So this is another one of those examples of something where you really should try to persevere and write stuff down on your paper, even if you don't feel like you have the full solution. I think a lot of times people feel like this is all or nothing, and that, oh, if I don't know how to do the problem, I should just not do anything. Really, you're going to get a much higher score if you tell me everything that you can tell me. Obviously, it needs to be relevant, right? If you come over here and write down the pigeonhole principle or something, I probably won't give you any points for that because it's not what this problem is about. But if it's relevant information, I can give you some points for that. Okay, guys, I have to do a review session for my other class in 50 minutes from now. I'm going to be busy for the rest of the afternoon with that. But I'll be back later tonight, and then I'm doing another review session. What time is it tomorrow? I think it's from 12 to 3. So I'll be back here, probably in this room again from 12 to 3 tomorrow, and we'll try to knock off, I should have crossed this one off. We'll try to knock off some of those other ones that I didn't cross off there, and we'll get most of the way through the review session. So guys, with that, I think I'm going to sign off.
A quick question before you go. For the schedule for coming in Monday, Tuesday, yeah, what times do we come in for the writing in the
In
part?
my final exam review packet, I have all of the office hours spelled out. You can come to any of those office hours.
Gotcha. Okay, thank you.
Okay, thanks. Bye, everyone.
Bye. Thank you.
Thank you.